Training and inference represent two distinct phases in the life cycle of an AI model. Training is the phase where the model learns patterns from data, while inference is the phase where the trained model is used to make predictions. Understanding this separation clarifies how AI systems are built, deployed, and maintained. The distinction matters because training and inference involve different costs, risks, and responsibilities. Training is expensive and complex, while inference must be fast and reliable. Confusing these phases often leads to unrealistic expectations about how AI systems behave in real-world settings. Training is the process by which a model learns from examples. During this phase, the model adjusts internal parameters so that its outputs align more closely with known correct answers provided in the training data. Learning from examples means the system does not receive explicit rules. Instead, it observes input-output pairs and infers statistical relationships that allow it to generalize to new cases. Parameter adjustment lies at the heart of training. Each parameter controls how strongly certain inputs influence outputs, and training seeks values that minimize error across many examples. Most training processes require labeled data. Labels provide the reference outcomes that allow the model to evaluate whether its predictions are correct or incorrect. Training is iterative. The model makes predictions, measures error, adjusts parameters, and repeats this cycle many times until performance stabilizes or reaches an acceptable level. Loss functions quantify error numerically. They provide a clear objective that guides learning and ensures improvements are measurable rather than subjective. Optimization algorithms use loss values to determine how parameters should be adjusted. These algorithms are designed to reduce error efficiently without destabilizing learning. Training is computationally expensive. It often requires large datasets, powerful hardware, and long processing times, especially for complex models. Training may take hours, days, or even weeks, depending on model size and data volume. This time, cost limits how frequently models can be retrained. Specialized hardware such as GPUs or distributed clusters is commonly used for training. These resources enable parallel computation but increase cost and complexity. Training data defines what a model can learn. If important patterns are missing, the model cannot infer them regardless of algorithm sophistication. Data quality strongly affects training outcomes. Noisy, biased, or incomplete data limits achievable performance and reliability. Overfitting is a key risk during training. A model may learn training data too precisely, reducing its ability to generalize to new situations. Validation data helps detect overfitting. It provides feedback on performance outside the training set while learning is still ongoing. Training typically ends when improvements diminish or predefined criteria are met. At this point, parameters are fixed and the model is considered trained. Inference begins after training ends. During inference, the model applies learned parameters to new inputs to generate outputs. Applying the model means feeding it features and receiving predictions. No learning occurs during this phase. Parameters remain fixed during inference. The model does not adapt or update itself based on new inputs. Inference is much faster than training. It is optimized for speed so predictions can be delivered quickly. Inference requires far less computation. This efficiency allows models to be deployed widely, including on consumer devices. Many applications require real-time inference. Delays can degrade user experience or system effectiveness. Inference often operates at massive scale. A single trained model may serve millions of users simultaneously. Inference occurs in production environments. Reliability and stability become more important than experimental flexibility. Latency constraints shape deployment decisions. Systems must balance accuracy with response time. Inference accuracy must remain consistent. Unexpected behavior can undermine trust and cause harm. Errors during training and inference differ. Training errors affect learning quality, while inference errors affect real-world outcomes. Models must be retrained to incorporate new data or correct deficiencies. Inference alone cannot improve performance. Retraining is triggered by changing data, environments, or objectives. This ensures continued relevance. Model drift occurs when real-world conditions change. Performance may degrade if models are not updated. Monitoring inference helps detect drift and failures early. This supports responsible deployment. Human oversight remains essential. Humans must interpret outputs and intervene when necessary. Training is usually more expensive upfront, while inference dominates long-term operational costs due to scale. Cloud platforms often separate training and inference workloads. This improves efficiency and scalability. Edge devices typically perform inference only. Training remains centralized due to resource requirements. Security considerations differ. Training protects data integrity, while inference protects model access. Privacy risks arise during both phases but differ in nature. Inference must avoid leaking sensitive information. Inference failures can have immediate consequences. These risks require safeguards and testing. Responsible deployment includes monitoring, fallback options, and escalation procedures. A common misconception is that models learn continuously after deployment. Most do not. Models do not self-update. Retraining requires explicit action and oversight. Operational AI requires engineering discipline, not just model accuracy. Businesses must plan for both training and inference costs. Ignoring this distinction leads to budget surprises. Research focuses on training innovation, while production focuses on inference reliability. Inference often accounts for most real-world costs due to scale and uptime requirements. Design involves trade-offs between speed, accuracy, and resource use. Understanding these phases supports better system planning and governance. The key takeaway is that training and inference are distinct but interconnected phases. Next, we will examine labels and ground truth, which define how models learn in the first place.